All right. Okay, we're going to go from the top. Hi, welcome everybody. This is my name is Nicholas Crouch. I work in the Maths Learning Centre for the University of Adelaide. This is the Maths 1B revision seminar. I will take requests. Those people who are online, see a couple of people online here. Feel free to pop it in the chat. I'm going to make sure I open the chat and put it off to the side so I can see it. I will only look at it a couple of times, so I will forget. And if you guys notice someone put it in the chat because you're looking at the screen, I'm actually not. Just let me know, because or if I'm not showing the thing that I'm currently working on, for example, that would be really useful if you could sort of tell me about that, because I would appreciate that. So when we come to questions like the one I've got here, what we want to do is we want to not do the thing that says, I don't know what to do, and not write anything. Because you know something about eigenvectors and eigenvalues, don't you? And we all do. We've all sat through the lectures. We've all read the notes. We're going, all right. So this is where eigenvectors, eigenvalues are linear algebra. And so the answer is, what is the definition? All right. So the answer is almost always, what is the definition? So if I go lambda v, a times v is equal to lambda v, that is my definition. All right. That's the defining characteristic. Now, what that means is when I do something like, well, so this information is telling me that a times vi is equal to lambda I vi. And so that is, if you do nothing else and you tell me that much, right, you have done the first step to completion. All right. And you kind of know it's the first step. So, because the thing after marking thousands of exams through my life, thousands, one of the great things about my current job, no marking exams, is that people who do well write stuff. People who don't do well don't write stuff. Literally, you can almost mark based on the number of words they've written in their exam booklet. Okay? So if you've written, this is not entirely true. I had one person, going to digress for a story, had one person, tricky question, really difficult thing. And so there was like an integration by parts thing, and then you had to notice something about it and do like the right substitution to get the integral out. It was hard work. Anyway, this person had tried all sorts of things. They had done 2 full pages of different things, and some of them they've worked on, and some of them they've gone back to the beginning. And I'm reading it and like, wow. And like at the bottom of the second page, I'm like, all right, so it's very clear you have no idea what you're doing. And then I turn the page and he'd continue, and I'm like, oh no. And I was reading through, and then the last thing he'd written is, I have no idea what I'm doing. At which point I killed myself laughing and going, all right, well, as the 5 marks, you've done enough to qualify for 2 of them. We're going on. He'd written something. He'd done 2 of the things that I needed to see. I gave him 2 out of 5. Or I have no idea what I'm doing. I did everything I could think of. That's not the worst plan if you have time. All right. Maths exams, most people will spend more time twiddling their pen than actually writing with it. All right. And that is because there's not a lot you have to write. You can write a maths, like when I do a maths exam, it takes me about sort of somewhere between a quarter and a third of the time, because that's how long it takes to write out the solution correctly. But you guys take extra time to think about what's the right thing to do. If you know what the right thing to do is, put in all the steps. If you put in all the steps, you tell me what you're doing at each stage, it will not take you longer. All right. It will not take you longer. You do lots of small steps means you're not making mistakes. All right. So this is a really good example of, I don't know what to do. But I am told that I'm looking for, I want to say something about the eigenvectors and eigenvalues of this matrix where I know about the matrix A. So what I'm going to do, right, is I'm going to do A times V1, VI. Let's call it VI. But the thing is, I know that's going to be A times lambda I VI. But that means I can put that lambda out the front because it's a constant. And then I'm going, oh, hang on, this is lambda I, and this bit I can write as lambda I, VI. Lambda I squared, VI. Okay. Now, having done that, who reckons they know what the answer to the question is? All right. A lot of you have got that smile, like I don't want to actually say it, but I'm pretty sure I won't know what it is. All right. You can actually now go, so the and doctor, how cool is that? This is literally saying that if I have a matrix, if I know the eigenvectors and the eigenvalues of A, then the eigenvectors of A to the power n are just the same eigenvectors. I don't even need to prove this for you, do I? No. All right. So, and the eigenvalues are the same eigenvalues, but to the power n. And so this is this, and so for a question that we had no idea what to do with, this fell apart in one move, didn't it? This was a one-shot wonder. I did one thing to help me understand what it was doing. Started with the definition. I did one thing to help me along that path, and then boom. Basically it's all fallen out in front of me. Now you have to be in the moment to actually remember to notice that. All right. But if you've written down the definition and you've tried to do something to get to this thing, then it will happen. So many of the show prove type questions in linear algebra and in the exam will be state the definition, notice something. All right. And that will be it. Okay. I've lost count of the number of questions where people go, I don't know how to do this. And I'm like, I don't know either, but let's write down the definition and let's do the next most obvious thing. And the question has fallen out. So if I can get you to do nothing else today, but to make sure you write down the first step. And it's the first thing you should do. You shouldn't spend hours thinking about it. You go, oh, definition of this is this, write it down. All right. Don't take that time to think about what's going to happen, because you can write 3 or 4 definitions. I've done it. I've students come to me with this was the exam question. I've written like 4 definitions. I go, oh, now I see it. All right. I had to get through, there was 2 of them I had to see next to each other. I wrote them down, and when I've seen them next to each other, I'm going, this is what you're supposed to, this is the thing I'm supposed to notice. All right. So what we're doing is we're going to do a lot of things. You're going to write stuff that will give you the opportunity to notice the thing that's going to make this question easy. Okay. So this is a really cool thing. You did eigenvectors and eigenvalues this semester, right? You will get asked to do eigenvectors and eigenvalues in this exam. All right. There is one thing I know for absolute certainty. There has not been a semester where Maths 1B students have not had to do 10 to 15% of their exam, which is about eigenvectors and eigenvalues. All right. You need to know how to do it. So let's do this. We should maybe, I'm gonna make an assumption about whether you can or cannot do eigenvectors and eigenvalue stuff, and just find a 3x3 matrix in here and actually go through what might be a thing. I'm actually gonna do that. This is not actually in the exam. I am gonna start doing a thing. So for those people playing along at home, all the materials I do. So yesterday's Maths for Data Science recording failed. We don't know why. But all the recordings for revision seminars for Maths Learning Centre go off on our website, and we try to have them up on the same day. So this one should be available online today with the stuff I've written as well, but it may not happen. Okay, so let's try a matrix A. A is equal to, and so I don't know how this is going to work out because this question was not written. Yes, that is what you're supposed to do. Well done, thank you. So, okay, so the first thing we're going to do when we do something like this. All right, so we're going to find. All right, so quite often they don't get you to do this from the beginning anymore because it's too much work in an exam, but we'll go from the top because you want to be able to do this, all right? All right, so the rule is it's like lambda I minus A. That is equivalent to saying A minus lambda I. All right, it doesn't matter which one of them you are doing, okay? These are equivalent, all right? Because we started with AV is equal to lambda V, and so one is doing AV minus lambda V is equal to 0, and the other one is doing lambda V minus AV is equal to 0. They're the same thing, people, okay? So you will get the same eigenvalues and you will get the same eigenvectors. The only difference is the characteristic equation, if it's for this one, will be the negative of the character, like it will be of minus lambda rather than lambda. Okay, so it doesn't matter. And quite often I like doing this because it's easier to just write out to go 3 minus lambda, 0 minus 6, 1, 1 minus lambda, minus 1, 2, 1 minus 3 minus lambda. Okay, expand across the top. So we're going to go, we're doing like the determinant of that equal to 0, lambda minus 3 minus lambda by subdeterminant, 1 minus lambda, minus 1, 1, minus 3, minus lambda, and then 0 by something or other, so minus 0 by something or other, I'm not even going to write it out, and then it's like plus minus 6 by, take out the row in the column, 1, 2, 1 minus lambda, 1, all equal to 0. So one of the things I'm doing when I'm going to do this, and it doesn't always work, is I'm not going to fully expand into a cubic if I can help it. I may not be able to help it, but if I can avoid expanding all the way into a cubic, I will do that. So 1 minus lambda, minus 3 minus lambda, plus 1. And then minus 6 by 1 minus 2, 1 minus lambda. All right, all equal to 0. So I'm going to expand. So I'm going to leave this 3 minus lambda out the front. And this is going to get me lambda squared plus 3 minus 1 is going to be plus 2 lambda minus 3 plus 1. And then we're good. Minus 6. And then this is going to be 1 minus 2 minus plus lambda. Woohoo. Not actually what I was hoping for. No. So this is one of those things that may happen when you actually do horrible things. Lambda squared plus 2 lambda minus 2 minus 6 of lambda minus 1. Bother is equal to 0. So part of me is going, oh, that's not going to work out nicely. I am actually going to have to expand to a cubic, whether I like it or not. And trust me, I don't like it. Minus lambda cubed. So this is going to get me minus 2 plus 3. So that's going to get me plus lambda squared. That's 2 plus 2 plus 6. So that's 8 lambda. And here I'm going to go minus 6 lambda. And then minus 6 plus 6. Oh, equal to 0. Sweet. Awesome. So we're going to see this is going to be lambda by minus lambda squared plus lambda plus 2 lambda plus 2 equal to 0. So I kind of got lucky in that apparently those vectors are linearly dependent. Who knew? But also there's an easy factorization for that because the constant cancelled out. Sweet. All right. So, and then, I don't know. So this is going to get me, so minus 1 plus or minus square root of 1 minus 4 times 2 times minus 1 on minus 2. So 1 plus 8 is 9. Woo. So it's going to be like minus 1 plus or minus 3 on 2. So it's going to be minus 2 or 1. Sweet. Awesome. So I've got my 3 eigenvalues, 0, minus 2, or 1. All right. It's tedious watching me do this. All right, I'm sure. And you can do it. So I'm only going to pick one. Which one do we reckon? We should try minus 2. Lambda is equal to minus 2. All right. So what we're going to do, we go back up. Because we're literally solving this system, all right, we've got a value for lambda now. So we're actually just going to work this out. So we're going to go, it helps to work back from the matrix where we've written it out here. So I'm literally going to copy that down, but with lambda is equal to minus 2. And so that's going to get me 5, 0, minus 6, 1, so minus 2. So 1 minus 2 is going to get me 3, minus 1, 2, 1, minus 3, plus 2 is going to get me minus 1. All right. So this is augmented matrix getting me 0. So then we're just going to do the row reduction. I'm going to swap up this row. So this is an application of the, I'm just going to write out what I did at every step, right? So actually writing out what you did doesn't actually take very long. When you're doing Gauss-Jordan elimination, you can go, let's do this. So I did row 2 is equal to row 2, take 5, row 1, row 3 is going to be equal to row 3, take 2, row 1. So I got 0, take 15, so minus 15, minus 6, plus 5 is going to be minus 1. Thank you. Thank you. That's going to make my life a lot easier. So this is why you write it out, all right? Because if you make a mistake like that, natural fact, as a marker, I was told, if it's just a simple arithmetic mistake, you can forgive that, all right? And don't take off a mark. If you make lots of them, then we will take off some marks, but there's like a cap how many marks we take off for just doing the calculation wrong, all right? You're a math student, you should be able to do calculations. So we will take marks off if you get it wrong, but the first couple are kind of free. All right, unless of course you're going to get 100%, whereupon if you make aim, so the head of school when I first started said, so they wouldn't give me 100% for honors, so because it wasn't 100% perfect. So if it's not perfect, you don't get 100%. All right, which for first year maths is actually you can get 100%, but for honors you probably won't. All right, but what that means is if I actually change. If I notice someone is on track for 100%, I will start taking marks off for little things. All right. So there's this sort of this line somewhere around high distinction where the marking gets a lot harder. And so, you know, if so that I've actually got a distinction, I've got a way of distinguishing between sort of a low HD and a high HD. All right, so let's keep doing this. 1 minus 6 is minus 5. And I feel like I've made a mistake here, but that's okay. I've got minus 1, so that should be a 1. So this point in time, I'm going to stop and go, I fucked up, because this number should be 3. What did I do wrong? I copied that right. That one's right. That one's right. Why do I know I've got this wrong? That's what? I don't have a row of zeros. All right. This is actually really important. All right. We've actually chosen lambda so that this thing should have infinitely many solutions. I should get a row of zeros. All right. I'm going to go, whoops. I may have made a mistake. I'm going to assume I've made a mistake in calculating the eigenvalues. I'm just going to make a note of it, and I'm going to go, no point in, for you guys, all right, you can do this. This is actually a good example of I've made a mistake. Don't know what I did wrong. I'm just going to go, hey, I made a mistake. I'm going to move on. All right. Because I don't know that it's going to benefit you from me trying to work out where I made a mistake. So we can, but we know how to find it. All right. So the next thing we're going to do, so if we were talking about eigenvectors and eigenvalues, who knows what they're really going to do? They're going to give you your matrix A. Then A is equal to. All right. And then you go, all right, lambda 1 is equal to, I don't know, 3. Then you're going to go, determinant of A is equal to, let's say 15. All right. And they're going to go trace is equal to, I don't know, I'm going to say, I'm going to try this. I did this yesterday. I got it wrong yesterday too. Didn't work out nicely. So they're not going to tell you all of the eigenvectors or eigenvalues. All right. They're going to tell you some. This is I'm going to use the fact that the determinant is the product of the eigenvalues and the trace is the sum of the eigenvalues. And that's what I'm going to get you to use to work out the other eigenvalues. All right. So we've given you one. So we've got lambda 1, lambda 2, lambda 3 is equal to 15. And lambda 1 plus lambda 2 plus lambda 3 is equal to 7. And so interpreting this information, 3 lambda 2 lambda 3 is equal to 15. And 3 plus lambda 2 plus lambda 3 is equal to 7. A little bit of rearranging. So this is telling me that lambda 1, lambda 2, lambda 3 is equal to 5. And this is telling me that lambda 2 plus lambda 3 is equal to 4. Woohoo. All right. So maybe rearrange this. Lambda 2 is equal to 4 minus lambda 3. And then when we do this, we're going 4 minus lambda 3 is times by lambda 3 is equal to 5. We are going to get myself 4 lambda. I'm going to drop the 3 because it's going to annoy me. Lambda squared is equal to 5, which is going to be lambda squared minus 4 lambda plus 5. Who doesn't factorize nicely? Don't. Neither mine's there. Actually, I have a plan. Nobody thought about it. Okay, so in the end, honestly, in terms of guessing numbers, right, I'm going to go, yep. And so now I can go, so I can go lambda minus 5 and lambda minus 1, lambda plus 1. And that should be right. Sweet. All right, so I can now tell you what the eigenvectors are and eigenvalues are. All right. So the other one they've been doing a lot of, so the other thing they do is they will give you an eigenspace. So they will actually give you a matrix. They quite often, they will give you a real symmetric matrix. Why would we do, what is important about eigenvectors and eigenvalues when I say real symmetric? What does that give me? Sorry? Diagonalizable. So this means actually that, so the real symmetric matrices means that that the the dimension of the eigenspace is equal to the multiplicity of the eigenvalue. All right. So if A is a real All right. And so that means it's diagonalizable. And more importantly, orthogonally diagonalizable. All right. So the thing they're going to do is they're going to ask you to do what? They're going to ask you to give an orthogonal basis. Typically, what they're going to do is they're going to ask you to do it for a two-dimensional eigenspace. And if I am trying to find an orthogonal basis for a space of dimension or any space, what am I going to do? Gramm-Schmidt process. Thank you very much. I love a bit of audience participation. So far, lectures in maths in first year maths are not actually a big selling fringe show, but give it a bit of time, we can work on it. All right. All right. All right, let's try and do this. So if you watch David's the revision seminars, so who were the kid when you saw the TV show The Fairies? I think it's The Fairies. Yes, you know what I'm talking about. And there's only one way to tell the time in fairyland. So it possibly helps for this story to say that David has two daughters, which are probably about your age. And so when he came to going, there is only one way to find an orthonormal basis in fairyland. And I can't do the song, and so I'm not going to. But on one of the videos, David does. So is it worth me doing a bit of the Gramm-Schmidt process to talk you through what's going on, or are we happy to go, it's in one of the other revision videos? Feel a bit ambivalent about that. I feel like that's enough sort of, we could put up with that, this is again, okay, so vectors. When it comes to making up vectors, I am very boring. And I don't know what's going to be another one. I don't know. I'm going to go 1 minus 1, 1. I should have had more zeros in there because that makes my calculations easier. But I'm going to try and find an orthonormal basis for this. Okay, so I don't remember if they're supposed to be. Spelling is not my thing. I'm a maths lecturer. If you want to know how to spell, look it up in the notes. Kernel and range. Ooh, we might come back to kernel and range of a linear transformation in the not too distant future. Great plan. All right. See, this actual suggestion makes my life easier. Okay, so we're going to try and do this as quickly as possible. So one of the things that can help my life, right, when I'm doing this, is I'm going to go V1 is equal to 1, 1, 1. All right, if I'm creating an orthonormal basis from an already existing basis, one of the things that can make your life easier is choosing the simplest vector as the first one, because that's one you're going to have to use the most. All right. And so I'm going to normalize V1 to be 1 on root 3, 1, 1, 1. All right. I'm always going to leave that constant sitting out the front. All right. Because that is also going to make my life easier. So I'm going to go V2 is equal to, so I'm going to go 1, 2, 3. I'm going to go V2 dashed. All right. This is sort of going, hey, I haven't finished using it. Minus, and so then it's going to be the projection of this vector onto this vector. So we're going to go 1, 2, 3, dot with 1 on root 3, 1, 1, 1, times by 1 on root 3, 1, 1, 1. Now, the advantage of these things here is they come out the front, all right? So the reason I've done it this way is those numbers come out the front, and I can go 1 on 3. And suddenly I've got rid of my square roots. I'm not mucking around with a whole lot of fractions with square roots in them or whatever. Don't want to do that. Want to do as little of that as possible. Okay. And so then this dot product 1 plus 2 plus 3 is going to conveniently be 6. Woohoo. It's like I thought about doing this ahead of time, which for those playing at home, I did not. So I've got 1, 2, 3, take away 2, 2, 2. Woohoo, is equal to minus 1, 0, 1. Wow. That could not have worked out better if I'd actually planned it. All right. And so now my V2, I'm going to normalize 1 on root 2 of minus 1, 0, 1. All right. I'm going to follow this through and do the last one, which we may be about to find is not linearly independent. So the working version is going to be 1 minus 1, 1. Minus, so I'm just going to go 1 on 3 and then 1 minus 1, 1 dot with 1, 1, 1 times by 1, 1, 1. All right. So this is the projection of this new vector onto the first vector in my basis and then take away. So the sum of, and so we're going to go 1 on 2 and then 1, 2, 3. No, 1 minus. Try that again. Minus 1 on 2. Where's the 1 minus 1, 1 dot with minus 1, 0, 1 times by minus 1, 0, 1. All right, numbers 1 minus 1, 1 minus 1 on 3. So this is 1 minus 1 plus 1, so it's 1, 1, 1, 1. Sweet. And then minus a half. And this is going to be minus 1 plus 1. That's 0. All right. Sweet. No, it does not exist. And so this bit here, this says these two vectors, this vector and this vector are already perpendicular. All right. Woo. Didn't expect that to happen, but yay, thanks. That is actually if I was doing this, I'd be going, this is a great exam question because that's exactly what I want to do. I don't want to get you to do a lot of calculations. I want you to demonstrate that you know what you're doing. Okay. So exam questions, if you're doing, some of them do take a lot of calculation. So, but not always. So this is going to be 2 on 3. This is minus 1. So this is going to be minus 4 on 3. And this is going to be 2 on 3 again. Now, I'm about to do a thing. All right. So I want to times by a constant to make the length 1. This would involve calculations with the third. That sucks ass. So what I'm going to do is I'm going to times by a constant. And I'm going to have 2 minus 4, 2. I'm going to divide by 2 because that's going to make my life easier. 1 minus 2, 1. And then I'm going to normalize. Because the direction is the thing I'm interested in, I don't have to worry about keeping it. I can multiply by whatever number I want. And by multiplying by that 3, I save myself a lot of effort. Okay? A lot of cognitive load, possibly getting it wrong. Because the direction is the only thing I'm interested in, because I'm about to make the length 1, multiply by a constant. I've done it twice. And I'm about to do it again. Because I'm going to go 1 plus 4 plus 1. So I'm going to go 1 on square root of 6 by 1 minus 2, 1. Yes. Like you would literally go, so I'd make a note. I'd go, so I can just sort of go, if I want to, I can go only interested in the direction. So scale multiple, I can make, so I'll make a comment. You're like, we've grown up, we got grown up math now. And so we actually use words with our working. All right. I realize you're sort of first year, and so you're not really, you're almost there, but you want to get used to just saying, I'm interested in the direction, therefore I've multiplied by constants so that to make the calculation easier. All right. And literally in published academic papers I've seen, we've done some trivial steps to make calculations easier, and you kind of go, okay, sure. And I'm just, yeah, I'm allowed to do it. I'm going to make my life easier if I do it. So I'm just going to go, let's go from there. All right. So got my orthonormal basis. All right. Woohoo. All right. This incidentally turned out to be quite a good exam question. More asked than class, let me tell you. You might see something like this. The numbers are easy to work with. None of those steps of calculation were difficult, and it got you showing the process. This would be like 3 or 4 marks worth in the exam, and I've done it in about half the time. I've talked to you and done it in about, well, I've done it in about the time that it should take you to do an exam. Okay, it's not a difficult thing to do, right? And if you're not talking, it's an exam. You're not talking. I find it hard in exams because I narrate the story as I'm doing it. I think the people in the office think I'm crazy, but that's okay. I work with David. It's fine. So any questions about that? So Gramm-Schmidt process is definitely a thing. Let's maybe kernel and range. So, sorry? Kernel range, rank kernel. Sure. What I might do, so at some point in time, I go, oh, I don't know what I'm going to do. Okay. Can I do this without making, I can do this. All right. So the question from the sample exam has got like an F, which is going to take R2, so so they've actually done, they're going to do wonderful things. And so F of, I'm going to go U and V is equal to, I don't know, what do we think our linear transformation should do? 2U plus V. So I have to have 3 components, V minus U, and I don't know, 3V. That'll do. That looks like a thing. So it's similar, but not the same as. G is going to take 3 to go to 2. So there are some things that we can do about this. All right. I don't know, what have I got? So this is going to be G of X, Y, Z is equal to Y plus Z, and I don't know, X plus Y minus Z. Feel like that's it. All right. Always, if I just make stuff up, it could go terribly wrong. Okay, so maybe what we'll do is go find a basis for. Okay, so what would you do if you're finding a basis for the range of a linear transformation? Right, the matrix. All right, so strictly speaking, standard matrix for F. So F of X is equal to A times X. This is sort of saying A is my notation for the standard matrix of A for X, and A is going to be equal to F of 1, 0 and F of 0, 1. Okay, F of 1, 0 is going to be equal to U is 1, so that's going to be a 2, that's going to be a minus 1, and that's going to be a 0. F of 0, 1 is equal to, where have we gone? 1, 1, 3. And so A is going to be equal to 2 minus 1, 0, 1, 1, 3. So this is one of those things, right? Range of F is the all right. So we know the thing you know is the range of F is the column space of A. Okay. It's really important that we're specific about it though. A matrix doesn't have a range. A linear transformation has a range. A matrix has column space. A linear transformation does not have a column space. All right. So it's important that we be clear about which thing we're talking about. All right. That's one of those things like people go, is my matrix linear independent? No, it's not. A matrix isn't, a linear independence is not a property of a matrix. All right. Now, if you're going to talk about the rows or the columns, that's a different question. All right. So you want to say one of the things that makes a big difference to you getting things right more consistently is using the right words for it. It's basically learning mathematical grammar. Okay, so we want to be specific about the thing we're doing with this. All right, so range of F is column space A. You are allowed to go to. All right, equivalent statement. All right, so I can actually also describe it, give a basis for the thing. So, so the mistake people make is that they try and tell me that they will leave out that word span. All right. So the range of F is these two vectors. This is not true. There is infinitely many vectors in that range, not just those two vectors. All right. So it's important that you understand that when you're doing this, you want to say it's a basis. This is a basis, or these vectors, the span of these two vectors. All right. So it's again, the key part is like using the language correctly. All right. So because if you use the language correctly, then there's no ambiguity about whether you've got the answer right. If you're not using the language correctly, people are left to assume that you meant the correct thing. All right. You may have used most of the correct words in almost the right spot, but it's about making sure you put in some of those keywords that tell me that this is the range is a subspace. I need to make sure people understand it's a subspace. Okay. So kernel, maybe we should do the kernel of G. Sure, what the hell? All right. Again, so kernel of G is the all right. So G of X is equal to B of X. I'm still visible at the bottom. Awesome. And so again, I'm going to do my linear transformation. I'm going to do my standard basis sector. I'm going to cut to the chase a little bit. All right. So strictly speaking, B has 3 columns and 2 rows. All right. And so the first one is going to be 0, 1, 1. And the second one, 1, 1, minus 1. All right. The reason I'm doing kernel is in the range space. So it's a subspace in the range space. I can do this so what I'd normally do is I'd then go, okay, because I'm solving sort of this thing where I'm doing bx equals 0, I want to find the x. So I can actually do this. And so do my thing, swap my rows, 1, 1, -1, and then 0, 1, 1. I don't even actually have to go anywhere. I can just go, all right, let z is equal to t. That says y is equal to minus t. And that's saying x is equal to, we should do x plus minus t is equal to 0. So x is equal to 2t. And so the kernel span of 2 minus 1, 1. All right. So again, I'm expressing the subspace as a linear transformation. Okay. All right. Part of what we wanted to do for that is, yeah. So the actual question from the sample exam was find f composed of g and g. So in actual fact, if you read the way this question is worded, all right. So I've changed it to be different transformations, just in case you're going to do the thing. And I've done other things, but they've gone determine a formula for this, give the standard matrix for this. I'm like, okay. So what do you reckon I'm going to do, given what we've done? So what do we know about the standard matrices of the composition of linear transformations? Here, I couldn't quite hear you, but the standard matrix for the composition of things is the product of the standard matrices. So if I'm going, right, f composed of g by some x is going to be standard matrix for A, so it's going to be a standard matrix for f times by the standard matrix for g by x. All right. Now, so f was mapping R2 to R3 and g maps R3 to R2. Let's give it a go. All right. This is going to be nice. So sometimes they're going to do it the other way around, right? And you can do it the other way around, but nothing says I can't just work out the standard matrices, do the product of the standard matrices and go, hey, this is the formula. So I would, if I was doing this, work out the standard matrix, then use that standard matrix. There is nothing wrong with that. That is valid mathematical process. All right. And you are allowed to do that in the exam. I think this is one of those things that people sometimes forget. They're like, well, they didn't ask me that way. Like, it's not written in stone, people. Some of the Babylonian stuff is actually literally written in stone. But that's like, they did pi and root 2 and stuff. So they're actually, I don't know. So digress slightly for a second. Talking of things written in stone, one of the first guys to calculate pi to 17 digits. He was so proud of what he'd done, because it took most of his life to do back in 16, whatever it was, that he actually that was actually what he had put on his tombstone. So he had the first 17 digits of pi put on his tombstone. So there are some of these things, some of these mathematical things are literally written in stone. When you think about it, kind of cool. I'm like, I don't think I made that significant addition to mathematical understanding that I really feel that anything I did should be put on my tombstone, but also, you know, hey, maybe it's the best I'm going to achieve in my life. So anyway, some of the mathematics that we're working on has been around for this stuff, hundreds of years, couple of hundred years. All right. So they didn't do much in matrices. Matrices sort of exploded in the 18th century, 18th, 19th century. So, and with computers, matrices have gone big because computers do matrices. All right. So a lot of stuff wasn't actually expressed in terms of matrices. I think it was Lewis Carroll did a lot of work with matrices, actually. You should check with David because David is the one who told me that. And if I've got it wrong, it's because I've just misremembered what he told me. So we said A was this matrix, 2, 1, minus 1, 1, 0, 3. And this one, 0, 1, 1, 1, 1, minus 1. And so this should give me a 3 by 3 matrix. Cross the row down the column. And so 2 plus 1 is going to be a 3. 2 minus 1 is going to be a 1. 1 minus 1 plus 1, 0, minus 1, minus 1, minus 2, 0, 3, 3, minus 3. Sweet. All right. I can then go f composed of g of x, y, z. I can use this to go, hang on, this is going to be equal to, so x plus 3y plus z, x minus 2z, and 3x plus 3y minus 3z. All right, I can still express the answer in the way they've given me, but I've done it quickly and easily with working out the standard matrix because I've done the standard matrix already. And even if I wasn't, I possibly would have calculated the standard matrix because I know this bit's going to be so much easier. All right, so I'm quickly going to do the other one because I wanted to, there was a reason, I have a plan. I know quite often when I sit down to do these things, I don't have a plan, but right now I have a plan for about the next 3 minutes. So, you know. All right, so we're going to go 0, minus 1, minus 1. 0, 1, 3, that's going to be a 4. 2 minus 1 is 1. 1 plus 1 minus 3 is minus 1. We expect a 2 by 2 matrix. Okay. All right. Can you give me a vector in the kernel of f composed of g? This is worth 1 mark, people. It is a yes or no question. Hands up those who think they can give me a vector in the kernel of f composed of g. All right. Are you watching this? So we know, we go back up here. This is in the kernel of G. So I've got this the wrong. So f composed of G. So if I do f of G of this vector, 2 minus 1, 1, I'm going to write this as A times B times 2 minus 1, 1. I know that B times this vector is equal to 0. Yes. Yes, I did that to you. All right. Did we see how cool that was? All right. You know stuff. So I've set this question, and okay, this when I said I had a plan, I actually literally had a plan. You know stuff about this. All right, this is actually some of those things that we're going to use. We've got this composition going on. All right, so the reason I've gone here is we know that this transformation cannot be invertible. All right, I took R3, I mapped it to R2, and then I mapped it back out to R3. All right, so we know because of the way G is, we know the kernel has to have dimension 1. All right, this is that rank theorem. This is so back here. So if we look at rank theorem so we should say G of X. All right, number of columns. N, number of columns, going to be 3. All right. And rank is going to be equal to 2. So rank plus nullity is going to be equal to 3. We know this can be 2. Best it can be is 2. It is actually 2. We can see that. So we know that the best it can be is 2. We can observe that those 2 vectors that would form that are linearly independent. So we can know that the rank is 2. But we also know that that tells me that the nullity must be 1. And so the dimension of the kernel all right. So this is actually a case where, okay, I can say, so is G composed of F invertible? All right. So this so it won't work with these. Right. It is F G composed of F is invertible. All right. But if I'd made the kernel of G dimension 2, for example, then the range of G would only be 1. It would be a very boring transformation, but we're going to ignore that detail. But that means when I do this composition, this will be that matrix will have determinant 0. Like the range of this thing will only be dimension 1, all right, because it carries through. Because the range of a composition of transformations is a subset of the range of the outer transformation. All right, it's a subspace of the range of the outer transformation. And so because G has a range of dimension 2, we've seen from looking at our rank theorem, we can know that it's going to have, that we're going to actually have, we could have. I have to check what happens when we do the composition. So it doesn't guarantee it. I have to actually look at the composition. So, but these are the sort of questions that we could be having that involve using that dimension and range and rank theorem. Okay? Some nice questions, people. I love it. All right, sure. I feel like I should write these down and send them off to Adrian for next year. I said that won't work. They're going to be a revision. Oh, that would be really funny, because if they got put in the exam, so under hypothetical, if they got put in the exam, the students who looked at the revision seminar from this year would see the same questions. Oh, dodgy plan. All right, sure. How we, anyway, okay. So, are people happy with what we've done so far? Sweet. Do we want to talk about anything else? Where to next? Sure. Yes, I can. Yes. So actually, this is actually one of the questions that you get in the exam that people find difficult. This can be one of the ones that actually causes the most problems because it can be very challenging. I should have brought a copy of Stuart down. And let's do it this way. We're going to go p of xy is equal to x times y minus x squared y squared plus 2. Okay. All right. I have no idea where this is going to go because I'm making stuff up. Sure. What works nicely? You know what? I think what we're going to do is we're going to, and so I can do x is equal to 1 on 1 plus t, and y is equal to I'm going to do that. Okay. Are we ready for this? All right. So I've actually done this so that I can go find dg dt. All right. But also dg ds. All right. So had an idea. Not sure if it's a good idea. Like I say, I have ideas. Some of them are good. Some of them, I'm going to say, I'm actually batting above average already today. So I think, yeah, we're due for something to go terribly wrong. We should remember to, it's really one of those funny things that I learned in first year was actually put some things on the top of every page, right? I got about halfway through first year when I thought, what I should do is first semester, I thought I should write up my notes. And then I realized I hadn't written what subject all the notes were on. And so I had this book of notes, which changed from like computer science, chemistry, physics, maths. And so they're nice and easy subjects to tell apart, well, except for physics and maths. And so, you know, like you can do it. But then I thought, you know what, if I'm half smart, what I will do is I will just write what subject I'm doing on the top of the page. Sounds like a plan. You should do that. Okay, so dg on dt is going to be equal to, so I'm going to do partial derivative of g with respect to x times by the derivative of x with respect to t plus the partial derivative of g with respect to x with respect to y. Y is defined in terms of two variables. And so I'm going to have to do it this way. All right. So state my rule nice and clearly. dg dx. Plan. I have a plan. All right. Keep telling me this. All right. We want to do all of these things separately. All right. Because if I write them out all separately, all right, then the guy marking it, all right, remember I've done a lot of marking. The guy marking it can go, oh, that one's right, that one's right, that one's right, that one's right. Sweet. Tick for the first step. Did I put it all together? Tick for the second step. Did I simplify it appropriately? Right. So this allows them to work much more easily. Now, people go, oh, I want to make it, I want to be a bit mysterious about what I did because I'm probably going to make a mistake. All right. The guy marking it's going to know. Let me be quite clear about you. If your thought process is I'm going to trick the guy marking it, then you're probably not smart. All right. There are very few students who've pulled the wool over my eyes when it comes to me marking their exam by not putting working in, because the answer was you didn't put something to tell me that you knew what you were doing, so I didn't give you a mark for it. All right. If you know what you're doing, you write it down. If you don't know what you're doing, you should write it down anyway, because the marker can at least see what you're trying to do. All right. If I've done this, then I can say what I'm trying to do. All right. I don't want to be hiding this from the guy marking it, because it's just not worth it. All right. Whereas if I put all the bits nice and clearly so that they can see what's going on, then I can do this. Now, if you've done differentiation so much like I have that you can do it without much thought at all, then you can just write them out. One of the tricks is, particularly with sort of functions of several variables, if you put the variables in alphabetical order, it makes it easier to determine if they're like terms. Okay, so it's a bit of a pro tip. Do it however, but then rewrite it so that all your variables are in alphabetical order so that it makes sense. So I've written it out more or less as is, but each term in this thing, I've made sure the variables have remained in alphabetical order. Putting it all together. So I'm going to do this in 2 steps. G of dt is going to be equal to, so I'm going to write out what this is. Y minus 2xy squared times by this thing. Minus 1 on 1 plus t whole squared plus this thing, x minus 2x squared y times by this thing, 3se to the 3t. This is not a final answer because I've got x, y's, t's, even s's in there. Don't want that. All right. So now I'm going to go, so this is going to be se to the 3t minus 2 on 1 plus t times by se to the 3t squared minus 1 on 1 plus t squared. And so you're starting to see why I think this is a terrible plan. Right, got a thing. Okay, that would be an answer. All right. The reason I've done this is a bit of a trick. All right. So when I'm doing dg by ds, all right. Strictly speaking, this should be dg by dx, dx by ds plus dg by dy, dy by ds. There is no s's in this formula. This term is 0. And so this simplifies down to just dg on dy times dy on ds. All right. And so I've got this already. So this is going to be equal to x minus 2x squared y times by, didn't write it out. E to the 3t. I can do that nice and easily. And so again, I'm going to write this as 1 on 1 plus t minus 2 on 1 plus t squared s e to the 3t e to the 3t. Now, sure, make sure I put it on. All right. So there is not much more I need to do about that. Okay. I can let that go at that point. Okay. Don't need to do any more. Hands in the air, walk away. All right. Because I could do a pile of things to simplify that expression. Pile of things. But it's not going to make a lot of value unless I'm going to work with it. Okay. And I don't want those, I didn't choose those things to be easy to work with. So, and so it's like you've got to remember in the exam is about you demonstrating understanding. All right. Demonstrated understanding, don't need to demonstrate the understanding of simplifying horrible expressions because there's a lot of horrible expressions in there that I don't need to do. So it's just a matter of you guys making sure that you sort of put all the bits and pieces in correctly. Okay. All right. Are we happy with that? All right. So, I don't know. We're gonna continue with G. We're gonna continue with G and do a little bit. So so so. Sure, I will do that. I'm just going to do a quick find the tangent plane thing. Keeping things simple. Okay, so tangent plane. So the normal vector is going to be partial of g with respect to x, partial of g with respect to y, and -1. All right. So I could go in, we're going to go z is equal to g of x, y. And so when I rearrange that to be g of x, y minus z is equal to 0, the partial with respect to z is just that -1. Okay. So literally all we did is we said z is equal to g of x, y. And so we rearrange that to say g of x, y minus z is equal to 0. And so this is just the partial derivative of that expression with respect to z. Okay, that's why this is. Now, my favorite plan is to do normal dot with x, y, z is equal to normal dot with a point. Okay, so normal is a vector, so we should do that. And so we should work this thing out. So first thing, P is equal to g of 1, 1, which is equal to 1 times 1 minus 1 times 1 plus 2. It's equal to 2. Awesome. Like I said, so my P is 1, 1, 2. Loving the plan so far. I hope this works out. Let's do this again. Partial of g with respect to x is equal to y minus 2 x y squared, and partial of g with respect to y is equal to x minus 2 x squared y is going to be equal to 1. So g partial of g with respect to x evaluated at 1, 1. It's going to be 1 minus 2 times 1 times 1 is equal to -1. Do you feel like this is going to be exactly the same? I do. So this is 1 minus 2 times 1 times 1, which is equal to -1. All right, so my normal is equal to -1, -1, -1. And so I've got my point P is here. So now I'm just going to do this. So it's going to be normal dot x, y, z is equal to normal dot P. That is going to be minus x minus y minus z is equal to this dot this -1 -1 -2 is like -4. All right. This is an equation. I can times through by a constant, specifically -1. I can say x plus y plus z is equal to 4. Okay, I can just do that. All right, makes my life a lot easier. So that's what I do for this equation. So yes, good plan. Love the plan. Everybody happy. Okay. And then, okay. So with that, so one of the things that, to sort of tie that up a little bit, differentiation is, there are some tricky things, but differentiation is recognizing how the function is put together. So I know how I can pull it apart to use the appropriate set of rules, okay? Partial differentiation can be difficult, particularly if I have rational functions or something, because I need to understand, is it a rational function with respect to this variable, all right? Or is it a composition of functions with respect to this variable? So quite often what they do is the question will have something that is composition of functions with respect to x, but not y. All right, so it's just a constant multiple with respect to y. And so that can be where you have different approaches to doing the derivative. All right, but differentiation should be at this level, give me marks. You should be possibly slightly stressed about making a simple mistake, but you should be reasonably confident to just differentiate at this level. All right, I give you a differentiation question, I'm going to expect 95% of the class to get 100% for it, okay? And so partial differentiation, finding myself here whacking in the tack on the equation of a tangent plane, bit of differentiation, I expect almost everybody to get it. Follow a simple formula, I expect almost everybody to get it. So I should be seeing, that should be one of those questions that everybody who's paid attention to what's going on so far can just do, okay? Okay, Taylor series. Taylor series. Who doesn't love a good Taylor series? All right, so there is a secret. There is a couple of secrets that we actually do tell you. It's kind of interesting if you read the lecture notes. They are in the lecture notes. Anyone got a function they'd like to do the Taylor series of? I know, it's a bit boring. You know what? I'm going to do something really dull. All right, I'm going to go f of x is equal to cosine of x at x equals 0. I'm going to do a Maclaurin series for cos of x. You guys should have seen this before. All right, should have. All right, and I'm doing something fairly simple because what they're going to get you to do in the exam is going to be reasonably simple. They usually only get you to do like a second or third order Taylor polynomial, and they want you to work with the error term. Okay, sure, let's do this. So we're going to go f of x is equal to cos of x, and so we want f of 0 is equal to 1. F dashed is equal to minus sine of x. F dashed of 0 is equal to 0. F double dashed is equal to minus cosine of x. F double dashed of 0 is equal to minus 1. I have a plan, and my plan is fairly straightforward. For completeness, all right. So I wrote out all these numbers because I'm about to use them in the Taylor series, all right? This, if you are asked to calculate an explicit Taylor series or Maclaurin series, do this, all right? These numbers here, all here. A, told at the start. N changes as you go through. This allows me to write out my series as going, okay, so it's 1. I'm going to go plus 0 by x minus 0 on 1 factorial. I know you're going, but why, Nick? Why would you do that? And then x minus 0 squared on 2 factorial plus 0 by x minus 0 cubed on 3 factorial plus, let's do one more, 1 by x minus 0 4 factorial. All right. That is literally what the formula is telling me. If I do that, I can just go, yep, sure, that's what my formula is telling me. This is going to simplify down to 1 minus x squared on 2 factorial plus x 4 factorial minus x to the 6 factorial plus x to the 8 factorial minus dot, dot, dot. All right. This is a well-known thing. You should know this. All right. This is a Taylor series you should recognize. Okay. Cannot be more specific than this. It is a series you should recognize. Okay. You should recognize that I can write this as a sum. So I'm going to go I is equal to, I think we want to go 1 to infinity. And this should be minus 1 to the n, minus 1 to the, I need to start at 0. And then I have x to the power 2i on 2i factorial. This is, yes, did I stuff something up?
Like the term x to the power 4 factorial, the third term, or the...
So I would call it the third term, but the power 4 coefficient, the quadratic, the quartic coefficient. So if I'm asked for a 3rd degree Taylor polynomial, that's that. Yes, and that is actually a thing they've done, not even a thing they do in the thing they have done in the exam. Give me the 3rd order Taylor polynomial for something like this. It's a quadratic. All right, it's kind of didn't get there. All right.
Where it wanted like
and so
and
so E4 corresponds. So if I'm and if I'm asking for E4, so E4, this is the n. So I'm expecting like f, and so this should be the 5th derivative evaluated at z, and then x minus a to the power 5 factorial. That is what that term should look like. All right. So when it's an error term, it's literally the next term, but rather than at a, it's evaluated at some z, which lies between x and a. So that's actually like, that's the beauty of what Taylor did, is he showed that for some value, there exists a value for this thing, which makes the thing exact. All right. Which is actually like, when you actually sort of look at, when you want to understand what's actually happening, that's actually super important. All right. And so because that says, that allows me to use that thing as bound for the error. And so if you've got to put yourself back in this time of, I don't have a calculator. I've like, if I want something done, I'm either doing it myself or I've had to go through it and train people who are questionable literacy skills. All right. School back when Taylor was around wasn't actually a big thing. All right. Most people couldn't read. So, getting reliable people to do actual calculations was hard work. And to do these things, you had to do lots of calculations and you needed someone to do it. Yes.
like the cosine series with that series of because x to the power 4.
Yeah, well, so the number here tells me the degree. And so that tells me that number. All right. So if I wanted the first, if I'd asked the question for the first 4 terms, all right, 1, 2, 3, 4, stopping there. All right. So if I'd asked for the not four, and I might have been a little bit more specific of non-zero terms, right? Because if I'm going to do that to you, I'm going to be a little bit more specific so that there's enough clues to make sure you're giving me the answer I'm asking for. Then I'm going to do that sort of thing for you. Okay. So it's really, yeah. So these are actually really important to sort of get your head around. We're going to be reasonably specific about the thing we're doing. Typically, they just say they will give you a degree. All right. So if I had asked for the degree 3 Taylor polynomial, well, say degree 5 Taylor polynomial for this series, I'm giving you asked for that bit because there's the coefficient for the x to the power 5 term is 0. And so this is equivalent to that thing. In actual fact, one of the exam questions was, give me the Taylor series of degree 2 for something like this. I gave you that. They asked about the error term. They said, what can you do to improve the error term? And it's about noticing that I could have, because the degree 2 and the degree 3 thing are exactly the same, I could use the error term for the degree 3 rather than the degree 2, and that gets me a tighter error bound. All right. So there are little tricks like that they may do on it. So if you notice they were alternating terms, they may be about to pull a trick like that. Okay. So it is about knowing what's going on with each of these things. Okay. Now, so I'm going to spend a second. And there's a thing on these. So one of the things I do when I do revision seminars is I go through your course and I make notes. All right. You should have already done this. All right. You should have everything of importance written down in one place. So if we look at mine are going to be considerably shorter than you because I've written down the heading because I know the course. I've taught this course. I've literally given these lectures, and so I know this stuff. But so my notes, I've written 12 pages of just a lot of it is just headings that I've included. All right. And so one of the things I did, so these are really rough stuff. These are Taylor series that we kind of expect you to know. Okay. I'm not sure that it's said explicitly that we expect you to know. I didn't read carefully enough to say that but all right, these ones I would put in the exam without any question. I would just go, yep, sure, they should be able to do that if they don't remember it. All right, you should have done all of these Taylor series and recognize all of them as we go. All right, because there is a trick. All right, the thing, like Taylor series, all good. This is beautiful. I can calculate a Taylor series. All right, there are two things we're going to do. If I'm putting a Taylor series question in the exam, there are two ways I'm going to take it. All right. One, I'm going to talk about how far, how many terms I need to get an error within a certain bound. The other is composition of functions. All right. So I'm going to leave that there for a bit longer. But because Taylor's theorem says the Taylor series is equal to the function, if I can see that my function, I know, e to the x squared, for example, I can calculate, so I will ask you for the Taylor series of e to the x squared. I can do it because you're supposed to recognize Taylor's theorem said it's equal. And e to the x squared is e to the x composed with x squared. So to get the Taylor series for e to the x squared, what do? I do that simple composition. All right, everybody had enough time to get this down? Yeah, if they want. So if I'm doing the Taylor series for e to the x squared, whoops, good. So the reason they do this is one of those questions that separates the high distinction students, right? Because I know that's like my Pn of x or Px is going to be equal to, and I'm going to do this. It's just going to be I is equal to 0 to infinity, minus 1 to the I, and then I'm going to go x squared to the 2i on 2i factorial. It is that simple. All right. It is really that simple. All right. If I can work with this expression a little bit. Summation I is equal to 0 to infinity minus 1 to the I, and then this is x to the 4i on 2 factorial. Oops, put two factorial symbols in there. Let's ignore that bit. Cool. And so I could actually, all from here, 1 minus x to the 4 on 2 factorial plus x to the 8 on 4 factorial, so on and so forth. All right. I can literally do that. All right. And this is a thing, this is actually one of those people where the comment I get from people who have done the exam in the drop-in center is, I had no idea what they expected me to do. All right. And so I'm telling you quite explicitly that one of the things that I might try and get you to do is understand Taylor series. So this is saying to you, when you do this, you're saying to me, I understand Taylor series says this series is equal to this function. If this function is a composition of this function and something else, then the Taylor series associated with that is just the Taylor series associated with the original function composed with that other thing. I literally just did that composition. Okay. That is all I have done. Okay. Yes. Oh, so see how the sign's changing? So because my terms are alternating sign, so in actual fact, usually when I see the alternating sign, usually I go, it's got a -1 to the power, index. And then the first thing I do is I go, okay, so I check I literally go through the first two terms. I is equal to 0. That would mean this is equal to 1. Positive term, that's right. Second term, I is equal to 1. Negative is out the front. Yes. So this is this should hopefully I've written it correctly. Hashtag occasionally make mistakes. Particularly, my supervisor used to say that, that's right. That is, and so like I say, I wouldn't, back when I did first year maths, I was expected to know those. I wasn't just expected to be able to work them out. I was expected to know them. The lecturer expected that that the asking me to write down the Taylor series for cos, sine, e dx, and log of 1 plus x was just me writing down the answer, not working it out. It was writing it down. Okay. And so, and that expectation has softened, but not that much. All right. It won't be worth a lot of marks to give me the Taylor series for one of those functions. You should know it. You should basically know it. All right. So yes, it's hard work, but also it's nice and easy thing to do. Okay. Is that all right? Now, so that's sort of the one of the thing that I don't think is made enough of in the course when you're doing it. So that's why I've actually done that particular thing. Do we have any other questions? Oh, where's the icon? Oh, I chose I as the, so just because where the I is actually, I've chosen I as the index for the summation. It doesn't have to be I. But because it's a summation index, I is my first thought for a summation index. All right. You don't have to express a Taylor series in a nice summation like that unless they explicitly ask for it. Okay. Doing this will probably be enough to get by. I don't mark the exam, so I can't tell you that is accepted, but it will depend on what. So, but there will be usually if I want you to write the answer in summation notation, I will say write the answer in summation notation. Yes. Did I write that? No, EDX. So, EDX is really, which pause momentarily and just do EDX. Let's just like e to the x. So if your f of x is equal to e to the x, and you're doing f of 0, that's going to be 1. But the thing is, the nth derivative is just going to be equal to e to the x. So the nth derivative of 0 is all going to be 1. All those coefficients are 1. And so when you take that summation, sort of fa, got my n there, n is equal to 0 to infinity. Yes, I know I've just swapped to n rather than that, than I, but that's okay. It's a summation index. This number is 1. So this is just x to the n factorial. All right. So I can just, I'm like, literally just write down what that thing is. All right. Yes. Oh, so did I do that? Oh, yes. Yeah. You know what I've done? We should do that. We should go, oh, that was the wrong thing to do. What we really should have done is we should have done e to the x squared. And so it should have been this one. Should be summation infinity. N is equal to 0. And this is like x to the 2 to the n factorial. So, see what you're talking about? Yes, that's a really important thing. Yes. Come on, people, wake up. More of you should have been onto that. All right, no, I expect to see half of you people onto me. All right, I make mistakes. You should have realized that I put in e x squared into it's the cosine, not into the e to the x one. All right, this is what I mean. Like they were trying to think of too many. When one day you're going to do this, or maybe you're not. But when you're presenting, you're thinking about a lot of different things, and you do stupid things like that. And I was never very good at not doing it when I was an undergrad, and it's got a lot. We should be clear, it's got a lot better, but there's room for improvement still. Okay, so we're nearly at 11. Do we have more questions? All right. This is where I remind you, all our revision seminars have gone online. David has done a lot of them. I've done. So what you get, you get different things from talking to me as you get from talking to David. All right. One of the joys of working together because we both have similar views about how maths should be taught, but also we think about the things that are important in a slightly different way. And so some of these things, you would have got a different version from David, but you've also got David's version online. All right, there are revision seminars from, and I think, so, you know, hashtag the university screwed us around and lost half our revision videos. But that's because I'm not sure you need revision seminars from 2009. So, you know, there is a lot. I can't remember when they start. Hit our resources page, Maths Learning Center, resources, go find Math 1B, pile of videos. All right. If there's something from 1A that was built on, then you've got the 1A video, the revision videos right there as well. Okay. So this is also to say that we are available in the Math Learning Center. David and me are actually busy today and tomorrow doing revision seminars because I've got another one in half an hour's time for Maths 1M. But I'm going to say good luck with the exams. All right. Just remember, the thing I want you to do is if you don't know what to do, write down the definition of the thing you're talking about. Write down the information being given. Write down all the things you can think of that are relevant. And quite often, like that very first thing I did, the answer just fell out from a very, very simple, this is the definition. This is going to help me work out what's going on. Okay? Good luck with the exams, people. All right. Thank you. Thank you to everyone online too. Stop recording.